Assalamualaikum and good morning everyone. Today I will present a numerical simulation of flow and vortex structures around a simplified car model. My name is Technologist Haris Rashidah binti Abdullah. I'm from Polytechnic Banteng, Selangor. My presentation is include introduction, theoretical background, methodology, result and discussion, and also conclusion and outlook. Introduction. Aerodynamics is essential for performance, handling, and stability of a car. The drag depends on flow field and it is very complex in turbulence area. Turbulence area normally happen in rear area of the car and it cannot be seen in experimental. The separation flow is time dependent. The flow structure cannot be viewed in the experiment. Here is the video for experimental to see the streamline of the car, but we cannot see the streamline in the rear area of the car, which is a very critical area for aerodynamics. The scope for this study is to generate the unstructured grid using snappy heads mesh for Osmo model and case domain. Run simulation in the steady and transient state using runs and hybrid runs LES. Validate the drag coefficient and pressure coefficient value with experimental result from the Daimler and Volvo. And investigate the influence of different model and inflate velocity. Construct the flow structure of the flow. Theoretical background, which is in the literature review, model comparison. In runs, we resolve the average, and in U-runs, we resolve the big vortices. In LES, we resolve the smaller vortices. Hybrid is combination between U-runs and LES. We resolve the big and smaller vortices, and in DNS, we resolve all the vortices. But in DNS, it uses the very high computational cost. So in this experiment, we use runs, unsteady runs, hybrid runs, and LES. So for the model we use in this experiment is K epsilon, K omega SST, Spalart Amaras, IDDES, and SLH. They have their advantage and disadvantage, which is K epsilon is good in a high RE but bad in near wall. K omega SST is good at free flow and near wall but depend on Y plus. The Spalart Amaras good in low RE but bad in a free flow, and IDDES is can resolve the log layer mismatch but use high computational cost, and SLH reduce the grid induced separation but also high computational cost. In this experiment, we have three steps, which is pre-processing. We using the open form, we generate the geometry, and we done the computational domain, grid generation, and we set up the initial and boundary condition. After that, we go to the solver, which is using also open form. We analyze it using steady state, which is using K epsilon model, K omega SST, and Spalart Amaras. But in transient, we using model K omega SST, IDDES, and SLH. For post-processing, we see the result using the para view. We see the pressure coefficient in rear section. We see the velocity around the osmo and flow structure around the osmo and also LES region. This is the geometry for the osmo model. Which is top, front, side, and rear. This is computational domain. This is 2 by 2 and the total length is 9 meter and it's from 4 meter from the inlet. Here is the grid we generate for this model. We use a smaller grid near the car and the smallest at the critical area, which is the turbulent area that we want to study. Here, the drag coefficient against number of cell graph, we use to decide the number of cell we want to use, which is we use 3.8 million number of cells for fine and 1.6 million of cells for coarse grain, which is near the Volvo and Daimler result. Here is the initial and boundary condition we have calculated for the case 50 meter per second and 25 meter per second for inlet velocity. Here is the result for lift and drag coefficient, which is, you see the CD here, and this is the experimental result. For steady state, we see the K omega SST give the best result near the experimental result, and for K epsilon is too high and for Spalak Amaras is too low. However, it's not very accurate because it's a steady state. And then in transient state, we can see for 50 meter per second, the IDDES give the best result, and for 25 meter per second, the IDDES and SLH give the best result near the Daimler and Volvo. We can see here the pressure distribution at the rear area of the car, which is for velocity 25 meter per second, the only K omega SST give a not very accurate result, and in this for 50 meter per second, the SLH give a different result, but IDDS give best result for both 25 meter per second and 50 meter per second. Velocity for steady state, the K epsilon give the best result because it goes in turbulence area, which is rear area of the car, and smaller Amaras give unsteady result because it not good in turbulence area. For the transients, the result is nearly same for all model. For the flow structure, for 25 meter per second, the SLH and IDDS give a good result, but not K omega SST. But in 50 meter per second, only IDDS give the best result. We will see why the result for SLH is different for 25 meter per second and 50 meters per second. And the K omega SST only resolve the big vortices. Here, the answer why SLH give not good result for 50 meter per second, because in the turbulence area, it's only using the RAS model, which only can resolve the big vertices, but in IDDES, it use LES model, it in resolve the rear area. Conclusion and outlook. Conclusion: K omega SST is the best model for steady state simulation. IDDES is the best result for transient state simulation, and SLH result depend on the velocity of the flow. Outlook: we can do improvement of SLH model so that we can use LES in the rear area, which is turbulent area, to increase the good result, and we can use to study the different angle of diffuser for the Osmoka model. That's all. Thank you.